и у него нет какой-то конкретного срока годности. Здесь есть в таблице Electrical Data Typical есть характеристики, насколько они ухудшаются со временем. И вот эти характеристики мы используем во время наших дизайнов. Можете сюда посмотреть. Так, я тогда возвращаюсь к...
Да. Я просто хотел сказать спасибо.
Да. So we continue with the next chapters about onboard computers. So there are several requirements which we are taking into account while designing. So there are operational requirements, functional and interfaces and protocol requirements. From the operational requirements, it's important to take into account operating modes of the computer and like draw this phase diagram of different states of the satellite. The OBC shall be autonomous, fault resilient. It was a fault detection, installation, and recovery. From the functional requirements, there shall be system run control. So basically, OBC shall collect all the possible telemetry about the satellite, which is APS is not collecting, and run control over the states of all the modules. The control shall be done also not on the subsystem level. OBC shall process the clock, so that's the source of the clock on the satellite. It shall be input and output for the data processing. Basically, it can be applied in terms of attitude control algorithms. For example, the sun sensors data is processed and the output data of quaternions about the satellite orientation is on the output. It shall communicate with subsystems and all the components. It shall provide data storage and so on. Functional requirements can be really like mission dependent, and there can be a huge list of these requirements. Regarding interface requirements and protocols, it shall be compatible with hardware and software interfaces and standards and protocols of all subsystems. And it's also good when it's compatible with like basic satellite standards. These are hardware components of the onboard computer. In the core of the system, we have most of the time powerful microcontroller with a set of digital like input outputs to control like either switches or like other something else. There are several blocks of memory, program memory, data memory, and like general memory, which will be protected from the latch up. There's also the watchdog, power and reset, communication, and debug port modules in the onboard computer. Regarding interfaces and buses, there are several architectures which we are considering. So like device-to-device communication, that's normally done with the payloads when we don't want to include them into the main bus, and this can be as RS-232 or SPI, or it can be the bus architecture where there are several devices on the bus, which is already RS-485, I2C or CAN. So we use for like this centralized and decentralized architectures together in the satellite, depending on the payloads and subsystems profiles. With master-slave communication, you can get like 1 megabits per second on CAN or up to 60 megabits per second with SPI. So yeah, that's pretty much covers all the requirements for like high-speed data downlink or inter-systems communication. While in standard satellites, signals have to be transferred over the long distances. Harnessing in the CubeSat is pretty straightforward and pretty short and pretty simple. So there is no need in additional like isolation to increase the length of the cables. For distributed architectures only, and here like you can see the example of the CubeSat. There are a couple of specifications proposed, this mill and Tokyo passing. But in terms of their utilization, like you can see point-to-point connections, this one can be used. However, even though there are like many protocols and many like physical layer protocols are available, most of the CubeSats are using either I2C or SPI or CAN buses. Yeah, so that's the simple architecture of the CAN bus. Or RS-232, we're mostly using with the payload providers. We have like quite sophisticated CAN protocol, which not all the payload providers can follow. Thus, RS-232 is like much easier for them to install in their systems. Some of the responsibilities of onboard computer is the measurement and storage of housekeeping. So the parameters which are not collected by EPS are measured and stored in the OBC. It's the main, it's the master of the CAN bus. It's the master of like I2C and SPI bus. And like it's also handling the CAN bus. It stores several software images, and for example, in our architectures, OBC is normally storing 3 software images, where there is a possibility to update one of them, and in this case, have the reliable software update feature. And execution of software tasks, for example, processing intercommons and telemetry, navigation and attitude control tasks. If there is no dedicated navigation and attitude control system on the satellite at that moment, OBC can also like handle them. Monitoring of health status of the payloads and managing the satellite modes, running the real-time clock, and performing the software update features. Again, let's consider like the block diagram and to see the example design of standard onboard computer. The core is in the microcontroller. It has several memories dedicated for either storages or for advanced computations, so SRAM and the flash memory. Normally we have, first of all, redundant flash memory, and we also like put the cover on the PCBs to save it like from, to provide some security from the radiation. There's the same watchdog architecture with a main switch to protect from the latch-ups. There's a internal flash memory, like not internal, but the flash memory dedicated for only the satellite purposes, while this one is dedicated for satellite purposes, while this memory is more like performing as mass memory storage for payloads. There's several analog to digital converters which are taking the, which are in charge of telemetry collection from the satellite, and also 2 transceivers for 2 redundant CAN buses. Key components of the satellite, its microcontroller is ARM-based, 32-bit RISC architecture. The clock is 60 megahertz, which can be boosted up to 180 megahertz. Has 12 kilobytes of static memory, 248 kilobytes of non-volatile memory, plus like 16 megabytes and plus 4 megabytes, and dual CAN bus connection. It has 3 external converters with 16 channels each. It can monitor external supply voltages. It has external watchdog with a shutdown capability. It can be programmed either via SPI or GTAC, and it's pretty low power, which is 150 milliwatts only. So that's a pretty efficient architecture in terms of computational capability, memory capability, and power characteristics. Regarding the housekeeping, this OBC can do 24 currents monitoring and 4 sun sensors handling. It monitors 2 voltages level, 8 additional currents from payloads, 3 rotational rates, 6 magnetic fields vector components, and 11 different temperature values. These are basically the telemetry values from the satellite for the mission, for one of the missions. Housekeeping is stored from the PCU, TNC, and PDH. So it's using the external memory for that. Basically, OBC is collecting its own telemetry, PS is collecting telemetry about the power consumption of all the satellite modules, then transferring these to OBC storage, and OBC stores all this housekeeping data inside. This was the first prototype of the onboard computer. So this was carrying 2 redundant kind of architectures and redundant TNC module. It had like 3 gyros, one on the each axis, giving some information about the attitude determination, together with 2 magnetic field sensors. It had a debug interface and a set of connectors. And this is so if this also was the first prototype of the system, this is already like the final ready product. It's PC104 based. As for controller, STM32F4 is used. It has 3 non-flash memories with radiation protection, non-volatile space-grade SRAM, and native S-band transmitter support for high-speed downlink. So it was developed back in 2014. There are like several redesigns already to boost the computational capabilities and memory characteristic of the OBC. And as this onboard computer can be used only for like 1, 2, 3 unit CubeSats, like the versions we have right now can be already used for like bigger missions of 6, 2, and 12 unit satellites. This is the updated architecture, which, yeah, another region of the architecture, which you saw on this blue image before. The STM32 controller is in the core, and all the peripherals are located around it. So the flash memory, analog to digital converters, several other converters, watchdog, degrees of freedom sensors, and SRAM, real-time clock, and so on. Any questions about onboard computers? If no,
Can we continue?
okay. Yeah, communication system. Let's go briefly through CubeSat communication systems. Basically, the main task of this is to provide telemetry, tracking, and command capabilities for the satellite to safeguard the communication between satellite and the ground station. So subtasks of the system is to modulate and transmit the telemetry, generate and track the carrier, receive and demodulate the carrier, detect data bits, synchronize them, forward clock and commands to the main bus, and range reception and transmission signal quality. There are several architectures which are used in the CubeSat world. Point-to-point, it's either direct ground station and the satellite. It can be done via relay satellite. This architecture is not as spread as the direct or broadcast data communication. This one like almost not used with the CubeSats due to complexity of the communication system. Another approaches for point-to-point can be direct downlink during data collection. So that's the one we're using most of the time. Direct link after storage of data. This as for example, our satellites are mostly located in the polar orbits. We're not using, we're not having the direct passes over the ground station every time. Like, not every orbit gives us the access to the satellite data. So yes, sometimes the storage of data before the next communication session is required. Yeah. And we actually have used the broadcast to several ground stations in the past. That was done when we had like a little bit of trouble with our ground station. So our partner ground station was working for, like, we both were working on the reception, so the transmission component of our ground station was not functioning properly. So basically, on our side, we were mostly listening, and the ground station of our partners was also listening and giving the comments to the satellite. So I can say that the broadcast architecture was also a part of my experience working with CubeSats. Regarding the data relay, there are, like, once we go to this constellation topic, it's pretty hot, like, architecture nowadays. However, in the CubeSat like industry, I think this is like overcomplication to the system design, and most of the CubeSats do not need this functioning. Like, if we're talking about the relay, so the satellite then needs to carry several transmitters, shall point, like, perform maybe complicated pointing maneuvers, which is in case of small satellite might not be needed. It's sometimes it's more like it's easier to utilize several ground stations than enhance the capabilities of the small satellites. These on this slide, you can see some of the key components of the transceiver, or the first version of the transceiver we were using. So it was at 90 CAN 102.8 based. It used CMX modem. Basically, we didn't have to do this modulation, demodulation in external circuits. The transceiver was BK77, and it also carried 2 CAN transceivers to communicate with the main bus. Yeah, like, before we go to the transceiver redesign or mission design, we obviously calculate the link budget, and here you can see, like, the sample of the link budget we're normally doing. All right, the next system which we're gonna briefly discuss is attitude determination and control system.
Sorry, there was some questions on the
Yeah, sorry.
About which radio model or technology uses to communicate with CubeSats.
All right, so the most used frequency band, for example, is the UHF or VHF, and we're using, like, antennas, like monopole antennas, where the satellite does not need to be oriented. We're normally using 2 UHF modules to provide, like, the full coverage, like the full sphere coverage on the satellite. That's used for telemetry and telecom. And if we're talking about high-speed communications, the S-band transmitters or X-band transmitters are the most common. There are a couple of projects which are using K-bands. However, instrumentation for this high-speed bands is already much more complicated, and especially antenna design is much more complicated. If in X-band and S-band we can use still patch antennas or, like, helix antennas, K-band requires additional investigations. Yeah. Another really interesting technology, which is I think it's on technology readiness level 7 already, is optical communications, and that's actually my personal field of interest. Optical communication has, like, lots of advantages, and we will talk about it in the last parts of lecture. but it has like lots of advantages in terms of terminal size, power characteristics, and transmission speed, security, and so on. However, right now they're only like prototype modules built for this, and it's not like so widely spread. So the most used is still UHF.
And also about hardware, I mean, stabilization techniques on the CubeSat.
Excuse me.
Stabilization techniques. How the CubeSat stabilizes itself.
Exactly. That's what we're going to talk right now.
Okay.
Yeah. So attitude control determination system requirements. First of all, shall consider what point in orientations shall the satellite like be on orbit. And there are like a couple of modes which couple of attitude control modes. First one is detumbling. Once in orbit, satellite like gets some initial speeds around 3-axis, like some angular speeds from the deployment, and like taking all these forces into account, it's basically starts spinning once in orbit. And the first mode is to detumble it, to make it more or less stable and rotate around like one axis at least. Then the safe mode is the mode which will still allow the satellite to be oriented correctly. For example, if there are deployable solar panels, they shall still face the sun. In this case, the satellite can be tumbling, but the mission critical parameters shall be taken into account. Then there are inertial pointing mode, nadir pointing mode, and the most advanced target pointing mode. Here in the picture you can see inertial one is when the vector, like the z minus vector, is collinear. Basically, it doesn't change its orientation. In nadir pointing mode, satellite must track like the z plus of the satellite shall be always pointing the center of the Earth. And target pointing mode is the mode when the satellite is doing pictures or is connecting to the ground station. Basically, the satellite shall be targeting one point on the Earth. It's like on the design process, after all these orientation states were defined, operational modes of the attitude control system shall be defined. So there are 3 characteristics of that. First is the task, what for this attitude control mode is required. This includes like downlinking, targeting the some field or some spot on the Earth for imagery, and so on. Accuracy parameters, so how accurate shall be the pointing, and which sensors and actuators can be used in the satellite. So while defining these modes, the following principles shall be taken into account. So the spacecraft can be in 2 modes at the same time. Modes shall allow the design to complete conditions with the equipment the satellite has. For example, if there are magnetodoggers, obviously it's not going to be possible to perform 3-axis maneuvers. The position of spacecraft shall be completely controlled by the attitude control system, and each control mode can be controlled by commands, either from onboard computer or from Earth. Here are some of the examples of attitude control modes and their connection. So the suspend mode shall be reached from every state. From suspend mode, the next one is auto acquisition, and here we can go to damping. Damping only can bring us to large angular maneuver, and from there it's possible to achieve with a sign pointing, fix or rotate, inertial pointing, or nadir pointing. Right, here we can see like one orbit example and all these pointing regimes and how do they change in time. Yeah, so if you find this is the first suspend mode regime. So in this case, the attitude control starts performing like all actuators are disabled, and once we go to the next auto acquisition, which is here, this is the safe mode, and solar rays are pointing to the sun. In sun pointing mode fix, here you go. The solar rays are still pointing the sun, and attitude is internally fixed. In sun pointing mode rotate, the satellite is able to rotate around this axis, which is z axis. Yeah. Earth pointing mode is visualized here. So in this case, there can be some instrumentation pointing the deer, or some remote sensing operation can be conducted. In inertial pointing mode, you see the attitude is fixed. Basically, the satellite has the same attitude. Large angular maneuver is done here. So it was done in order to come to the sign point in fixed orientation, and in the damping mode, the rotation from earth pointing mode was stopped. Basically, here are the examples of how modes go from one to another. All right, just a second. After the satellite is in orbit, so there's no spacecraft basically attitude control. The simple spin stabilization is required because satellite is tumbling. Like the speed of tumbling can be really high and can influence even the communication with the satellite. The acquisition, so in this mode, initial determination of attitude is conducted. This mode can also be used to recover from power upsets or emergencies or breakdowns. In the slew mode, rotation of the spacecraft is defined with the safe regime, and it's combined with the restrictions of operation and power consumption. In Earth pointing mode, the satellite points to Earth in instruments, and the sun pointing mode, it points to the sun with largest solar area. So after all these orientation, pointing regimes, and pointing modes have been defined, we need to define like what's the accuracy and what's the mission requirements. So accuracy shows how well basically the satellite can point, and the range is defined by angular motions or accuracy, which can be held. This is yes, also an another 3 parameters to control at jitter. Once we're using some rotation mechanisms, there's always a probability that something will vibrate, and this jitter, for example, can influence the quality of imagery taken by the satellite. Drift, it's a low frequency motion of the satellite. We should also take into account once we are designing the attitude control system. And the settling time, it's the time when the satellite returns from the maneuver to this upset state. Yeah, maneuvers basically is the systematic change of orbits or attitude parameters. It is specified by angles, rates, direction, duration, and frequencies. An example of the slew maneuver can be like 180 degrees slew maneuver with the rates 1 degree per second around that axis for 3 minutes every day. The attitude of satellites is subjected to disturbances, and these are gravitational forces, atmospheric drag, solar radiation pressure, magnetic field, and some internal disturbances generated by mechanisms or rotating devices like reaction wheels. Also, important step in designing attitude control system is to define the coordinate system, and I think we know some really crazy examples when the launch vehicles were failing due to the fact that coordinate system of the launch vehicle was defined in the wrong way. So yeah, that's a pretty important step. Then there are several approaches to provide active attitude control, and there are several types of actuators. These are coils, flywheels or reaction wheels, and jet engines. After we define the control, the actuators, we need to also define sensors based on which we're gonna estimate the orientation and control electronics to control the actuators and collect the data from the sensors. This is for the active attitude control. For passive attitude control, it's possible to use the boom or magnetic stabilization, when just a big magnet is installed in a satellite. Here on this slide, you can see some of the typical sensors and their parameters. For example, internal measurement, U rates, data rates, they're pretty heavy and might not be utilized on small satellites and have pretty big power consumption, while sun sensors have much less of the accuracy, but they're much lighter and consume much less than 1 watt. Star tracker, they're also quite accurate instrumentation. Current star trackers are much less than 3 kilograms, especially like for CubeSats, and they're much less power demanding. The horizon sensors, magnetometers, or GNSS receivers, typical attitude sensors. A few, like really briefly, about the approach for sun sensors functionality. So the sensors we're using are these PSD sensors. This is the sensor. This is the hole, which is a hole, the through hole. Once the sun is passing through the hole, it leaves the shadow on the PSD sensor. Sensor generates currents, and based on the currents, we can evaluate these two angles and then estimate the 2 angles of projection on the sun sensors. There can be 7 digital sun sensors, and these openings can be done in a really advanced and a tricky way, thus giving more information, not just like several currents, but much more currents, and the precision can be much higher. Star tracker is pretty much the optical thing with SSD and microprocessor on the back, and the picture of the stars is compared to the picture of the taken by the camera, and misalignment is compared, and the angles also, like 2 angles are relative to each other, are calculated. Infrared earth sensors, you can also see the principle. So basically the infrared shadow or pattern of Earth is imaged using also the CCD matrix, and the deviation from the center is evaluated. Yeah, here you can see some advanced dual infrared sensors and their physical diagrams. In terms of attitude control performance, there's a normally pretty simple controller. We have desired attitude, we have the attitude measured by the sensors, we feed the signal to controller, which controls actuators and changes the spacecraft dynamics. There are several ways to provide the stabilization. The most used one is the 3-axis, and this covers most of the applications. This can be done using the flywheel, reaction jet stabilization, momentum wheels, reaction wheels, stabilization control, momentum gyres, or solenoid coils. And in this one, you can see the summary of the stabilization types, the accuracies, and some remarks. For example, spin one is pretty passive, simple, low cost. Reaction wheel-based stabilization has higher accuracy, higher flexibility. It's possible to perform quick attitude changes. However, it's a little bit, it's more expensive, and the better jitter and vibrational profiles from reaction wheels are, the more expensive they get. Body stabilization, it doesn't have pretty much flexibility. It can be accurate, but it's also expensive. Using the reaction jet, quick attitude changes of large systems can be done, but compared to the other types, it's like absolutely expensive and mostly not used for the small satellites. Gravity gradient is the less accurate from all of them. It's passive, simple, and inaccurate, but it's sufficient for some small satellite missions. This is the reaction wheel assembly, for example, we've been using in our projects. It's built by our partner in Berlin. Yes, you can see here the 3 reaction wheels in the pyramid architecture. The integration of 4th reaction wheel provides the redundancy in terms, like if one reaction wheel is breaking, for example, there's another one to substitute it. Yeah, it's pretty compact and pretty small assembly and can be installed in CubeSats, like starting from 3 units and up to 6 units. This is also the star tracker, pretty compact and pretty small. It doesn't have a flight heritage so far, but pretty accurate and can be used on board of the small satellite mission. These are 2 reaction wheels for smaller and for bigger satellite, built by Hyperion Technologies. They built for 1 to 3 unit CubeSat. They have like all the electronics incorporated, like all the drive electronics. Yeah, so they're much. Yeah, so I think this one is for 1 to 3 U CubeSat, and this one is for 6 to 12 unit CubeSat. Like, not possible to see the difference, the sizes, but like it's already like observable once you see them in real life. And this one is the highly integrated, like a system which has first PC104 form factor, several reaction wheels installed in one platform, and the star tracker together. So that's like already the attitude control solution with all the required sensors and instrumentation installed. So that, I think, it consumes 0.5 volume of the satellite. And with this, we're coming to the last points of the second part of the lecture. This connected to space debris. There've been a lot of really a lot of CubeSat missions in the past, and we'll see later today how many constellations are coming and how many satellites are coming to the low Earth orbit. So people are becoming more aware of growing space debris problem. In 2002, on the United Nations have issued their recommendation that all the satellites shall be deorbited within 25 years after end of life. Some experts consider that 25 years is not fast enough. So CubeSats mostly occupy orbits around 500, like around 400 to like 600, and for the CubeSats which are above 550, orbital lifetime is normally like it takes more than 20 years. So including the amount of rising launches within this 20 years from now, the orbit will be really crowded. Additionally, general lack of propulsion and propellant on board of the CubeSats. Basically, CubeSats cannot perform mitigation maneuvers as the big satellites can do. And the short design lifetime. So CubeSats are normally developed within 1 or 2 years, and around 20% of them are failing. And once the satellite has performed its mission, most of the CubeSats are left without any control. As a consequence, which might come in the near future, of course, deorbiting might become mandatory. But here a lot of experts are also showing their skepticism because it's like really hard to prove if you're gonna do the orbit or not, even though if you have the orbiting mechanisms on board. There are several main deorbiting concepts available today. First is using the drag. This one has impact only on the orbits below a certain height. So like for the CubeSats where like on orbit more than 600, that might not work anymore. So the approaches here are sails or like big balloons. Another one is electrodynamic tether. So this one uses magnetic field and drag forces that can be utilized on any orbit, but I think it's not as efficient as the first one. And propulsion modules, they basically, the satellite needs to change its attitude, turn on propulsion, and decrease the orbit. Right. And let's go through like some of the examples of these systems. Here, CubeSat Terminator tape. It's a compact, lightweight module. It doesn't have to be powered up additionally. It has its own solar panels. Pretty small mass, pretty small size, independent, pretty easy. The only disadvantage, it takes the space from the satellite side, thus taking 2 solar cells away. And if we're talking about 1 unit CubeSat, 2 cells, it's already quite a lot. The balloon drag devices, another one, they augment the drag coefficient of the CubeSat, which leads to faster deorbit. Right, you can see on the picture basically this balloon. Propulsion modules, so this one is built by Aerojet Rocketdyne, has quite big mass, quite big size, and might not be suitable for all the CubeSat missions. Yes, and my favorite one is the sail, the huge inflatable sail, which increases the drag force. Sadly, all the missions which were carrying these sails, they didn't succeed, but technology readiness level is pretty close to 9, so technology is almost available. This is the sail. All right, so with this, my part of the presentation is finished, and we will jump on the communication constellations in the next, after the break.
Okay, so 10 minutes, it would be, with our time, 5 past 4. So by your time is
12.
12, yes. Окей.
Да.
5 минут первого будет, правильно? To'g'ridan 5 minut o'tganda ko'rishamiz.
Tushunarli.